Hello, welcome back for the part 2 of the recording on memory management. Let us take a small example and quickly go through that. Imagine I have a logical memory. So here I am going to assume little different from what is normally the ratio is or the difference is. Normally what happens, as I mentioned, logical memory or a virtual memory size, what the program assumes, is much greater than the physical memory that we have, okay, in the system. So memory management unit tries to give you the feel that you have so much of memory, but actually it is not. But to make the understanding of how a particular logical memory address gets translated to physical memory, I'm going to take a little different comparison, and it's not realistic in terms of actual use, but let us assume for our discussion purpose the logical memory is only 4 bytes of pages, which is naturally not normally done by any system. We don't have a page size of 4 bytes, but this is to make us understand how the paging system works. Okay, so I am going to have only 4 pages. That means I will have page 0, page 1, page 2 and page 3. Then how many bytes are there? 16 bytes are there in total. So the addresses would be, let me write it here, maybe in a different color. The addresses will be how many bits? Now the totally there are 4 into 4 bytes, right? 16 bytes. 16 locations are there. Now how many bits are required to address them? You need 4 bits. So let me write all of them 000 to 111. Okay. Now let us mark the page boundaries. Okay. What will be the address here? 0, 1, 2, 3. This is one page. Then I will start with 0, 1. This is 4th byte. Then I will have up to 7, right? So 0, 1, 1, 1. So this is another 4 bytes. The addresses are varying like this. Then the address will change over to 100 to this address. Okay, 1011. This is another 4 bytes. So let me number them 4 bytes, 4 bytes. Then from here it will be 1100 to all ones. This is another 4 bytes. So this is how the address is going to be changing. Now let us now look at this portion. Let me write it as B0, B1, B2, B3. If you see the lower 2 bits, why am I taking 2 bits? Because I need only 2 bits to represent my entire page, which is 4 bytes. If you see, look at the addresses of how they change. They all change from 00 to 11, then 00 to 11, 00 to 11 and 00 to 11. So this is the offset within the page. When you have 4 bytes, it will be having 4 different values, which is nothing but 00, 01, 10, 11. And then offset within the page will also again change from 00, 01, 10, 11. So the offset is the address bits will change. The same number of bits are used and they will be changing from the maximum that it can represent, which is all the bits which are required to represent within the page or address all of them, and then it will start from 00. So what is the difference between this offset address, this entire address and this entire address? The page number, which is given as this next 2 bits. Okay, so let me name this 2 bits. Actually gives you page number. If you see this 00, it remains as 00. That means it is page number 0. Now this is 01, it remains as 01, so this is page 1. This is remaining as 10, which is page 2. This is page 3, correct? So effectively we are having the address which is varying from 00 to all 11 can be divided into two parts. Okay, let me call this m bits. Okay, and this let me call it as n bits. Why am I naming them as generic number? Because I may now decide to change my page size and the number of pages, and then the same logic will hold good. If it holds good for 4 bits of my address, it will hold good for 16 bit or 32 bit or 64 bits, right? So this m bits actually refers to the offset within the page, isn't it? 00 to 11 represents the offset within the page, which is going to be the same for every page. And how will I know which page I am referring to? The higher bits, which is the actually a page number, because it gives me 0 and 1 and 2 and 3. So in an address, if I give you an address and then say that the page size is so and so, then you need to identify the lower bits which are required to represent the page size. And then all the higher bits I would naturally be assigning it to page numbers. So all the combinations of that will give me the page number. But the page number is not going to change as fast as you think in the lower bits, right? So it will change on every page boundaries, because it's you are looking at the page number leaving out the offset bits. So remember, the higher order bits will not change so frequently as the lower bit, right? So since we are dividing it in the place where the offset is stopping and then the page number is starting, it will be changing once in page boundaries. Now the one good question to answer is, how do we know that it is changing exactly on the bit boundaries? It is happening because I make sure that my page size is always to the power of 2, some power of 2. Okay, in this case m, let me say page size is always, offset field is same as what I decide to have a page size as, and the page size is always to the power of 2. I can't have a page of, which I told you in the previous lecture, that I can't have 223 as my page size. It should be a power of 2. So here page size is 4, which is power of 2. So it actually fits well. By taking a small pages, it actually fits well and then makes you understand how it actually helps us in getting the page number out of the address. Which address? Logical address. Because why am I looking at the logical address? Because this is what my program assumes that it has that much of space. So this, how do I decide the number of bits? It depends on what the system supports. Okay, so logical address based on, as I mentioned, in Linux it is 3 GB if it is 30-bit processor, or if it is a higher 64-bit processor, much more than that. So the logical bits are decided by the OS with the help of course the architecture. So because you should have the registers which can hold that much of address, right? Because I told you that all the registers within the processor is holding the logical address, and whatever pointer address I get from my program is actually a logical address. That means it has to be stored in a register, because LDR, STR instructions of ARM actually uses those register contents. So the register should be wide enough to accommodate the logical address that I assume. So OS cannot assume that I will have logical address of now maybe 128 bits, and then the processor on which this OS or the task is running is of 64 bit, then it's not possible, right? So we need to have a sync up, or there should be a relationship between the processor where it is running and the OS, what it assumes the logical address of a processor is going to be, and that is going to be supported by the MMU also, because MMU is going to get that much of logical address. So it needs to be, page table should be there, and then it should be converted into a physical address. So this is the logic. I hope this is clear now. M and N bits, how they map to the page size and then the page number. Now this part is done. Now I want to translate that particular um, logical address into physical address. Now let us assume for our argument's sake that physical address is little longer than what I have for the logical address, okay, which is not normally the case, but let us assume so, okay. Now, as I told you that it is the page size and the frame size needs to be same. I am going to call them as frame when I am talking about physical memory, which is nothing but our main memory, which is normally made of DRAM. So frame number also will have frame 0 to some frame higher number. Now let me assume it is 50. Why 0 to 15 is 16 frames. Then you will be now able to tell me how many bits are required if I have this. Now what is the frame size going to be? Frame size needs to be same as the page size. There is no question about it. So this, if I am following a page size of 4, I need to have a frame size of 4. That means it's going to be changing from 00 to 11. Okay. Now you know m bits and n bits. M bit is 2 bits, which is 00. Fine. This, what is this n going to be? This is going to give me the frame number, because I am using this n plus m bits as the physical address to address my memory. Then I should make sure that all the locations in the physical memory I should be able to address. That means I should have sufficient number of bits in my address to access them. So since there are going to be 16 frames, how many bits I need? If it is 4, I need only 2. If it is 8, then I may need 3. But because 16 frames are there, I will need 4 bits here. Okay. Okay. Now we have come up with the number which is 4 plus 2. Okay. Which is nothing but 6 bits. Now is it correct? Now it's very simple. You can see that there are 4 bytes in each frame and there are 16 frames. So 16 into 4, 32. Sorry, 64. Okay. Now 64 bytes are there and we need 6 bits, which is correct, 16 into 4. So if that is the case, now what is the, which actually refers to the frame number and which refers to offset. So the lower 2 bits still refers to the individual entries or bytes within the frame, and the higher order bits, which are 4 here, refers to the frame number. So given this kind of a setup, now suppose if I am trying to bring the first page to maybe page 0 is sitting here, I brought it to frame 1. So let me maybe write it here as frame 1. Now what should be the page table entry? Now what is page table? I said page table is the one which translates every address into logical address into a physical address. Now this actually refers to the page number. An index is page number, and what you get out of it is the frame number, because what we need actually is basically where is this frame, or sorry, where is this page in the physical memory, which frame it is. I can fit it into anything because both sizes are same, and I don't need to worry about whether page 0 and page 1 are adjacent frames here. It can be anywhere. So for example, page 0 I am assuming it to be on frame 1. Okay, in that case, what is the entry into the page table first of all? How many entries I should have? I need to make sure that whatever number of pages I have, that many entries are there in the page table, because this is my address, and anytime my program which is running on the CPU would generate any of the addresses. Any of these addresses which are logical address space as far as my program is concerned. So I need to make sure that every address that I generate or my program generates from the CPU has some mapping in the page table. It need not have to have a frame assigned. Maybe it will have some frame which is not there, some page may not be there in the physical memory, then I can bring it, but I need to have an entry in the page table. So in this case, 1, 2, 3, that's all. I need to have entries for 4 pages. Now imagine that I have not brought any other page in the frame as except the page 0. That means page 0 is in frame 1. So if I have a page 0, page number as 0 here, I need to have frame number as 1, because if I generate any address which is lying within this 4 bytes, I will not use this lower bits to access the page table. I only use the top portion, which is the n plus m bit, the n part of the bits. Only I will extract out and then I will index into the page table. Okay, this I am showing the 2 entries here, but actually this 0 corresponds to 1 entry here. Okay, so the same thing, both are same. Okay, so I am having one entry 1, which is nothing but a frame number. Now this one actually takes 1 bit only to address, but since the frame number is 4 bit wide, each of the entries here needs to be 4 bits wide, because right now I have one which can be represented in 1 bit, but I may have a frame which is 15. Then I need to have 4 ones as an entry here. So I need to have the entry of 4 bits here as a frame number. The page table should have a 4-bit entry, because for ranging from 000 to 111, 4 ones. Okay, so now if I have this, what I will do? Okay, now suppose, how do I convert my logical address? Let me write it again. Imagine that the first address is 000. This is the page number, right? And this is the offset. Now I don't worry about the offset portion at all till I get my frame number from the page table. Then I will take care of the offset. Offset field will be taken here directly. Okay, it will not go through the page table at all, because page size is same as frame size. So I don't need to do anything with the offset field of the address, but I need to take care of the page number part of the address, index into the page table. And now in my case it is 0, so this is the first entry which has a 4-bit entry 000. Please remember, sorry, 001. Then what I should do? I should exactly extract this 4 bits and then append it. Okay, not adding. We are not adding to it, appending to the thing whatever address, because 00 is there, that offset field is appended. Okay, now this entire thing will be my address. Now will it correspond to the first address in the physical table? It will be. Okay, let me make it clear. Now this will be the first byte of my frame 1. So what is being done here is the page 0 has been brought here and kept in frame 1. So I need to generate the address from the CPU, which is interfacing with the, after the MMU, which is interfacing with the physical memory. Okay, physical memory. I need to give the address which actually corresponds to the address where the page 0 is currently in. So it is in frame 1. So I have generated the address by converting the page number into a frame number by having the entry there, which OS has already taken care of, because it knows that page 0 it has brought into frame 1. So it generates the address. Now one more example we will see quickly, and before we go to the slide. Now suppose page 1, which is this page 1, is in frame 14. Okay, frame number 14. Now what is the address I need to be generating if I have to get the mapping properly done? Now I am saying again 00. Suppose first byte of page 1 I am accessing. Now page 1 will have 01 and 00. This is the logical address I get. Now This 00 anyway I don't want to do anything, but I need to make sure that offset is appended to the frame number. Now this is the frame number part of it. Now what is the entry I should have if my page 1 happens to be in a frame 14? I need to have the entry here, okay, which is 14. Now what is the value of 14? It will be 1110. Now this entire thing will become my physical address, which will be the first byte of frame 14. Okay, frame 14. So what is happening is you divide the part of the logical address into offset and page number, take the page number and index into the page table, get the frame number out of it. The number of bits that of frame number depends on the size of your physical memory, how many frames are there. Then take that frame number, append it with the offset, you get the physical address generated. That will exactly map to the location within the frame. Now if suppose if my offset is 1, then I will access the next bit byte. If it is 10, then I will go in this. So I will not change this offset anything other than 00 to 11, which is within the offset field. But this gives me which frame it is mapped to. And this is about the page 0, and the same thing is true with the page 1 also, page 4, frame 14 also. Frame 14 is here, okay, which is page 1 mapped to frame 14. Frame number is here and offset within the page is here. Offset on the logical address is within the page. Here it is going to be within the frame. That's all. Because anyway the same page content is going to be copied into the frame. So it is done. So this, if you have understood, I think you will be able to appreciate what is going to be covered in this one. So I quickly show you some other example here. It's good that I took some other different example when we explained with the board. So power of 2, frame size and page size, they need to be same, and taking the logical memory which is same as what I showed you there. I think I don't need to explain this, but here frame I have taken it little differently. Okay, there are byte frame size is same, but here I am not having that many frames, so is little less number of frames here. Okay, these are all about the logical memory part, which I already explained. Now look at the frames here. Now frames are, how many frames are there? It is only 8 frames are there. So the page number portion will not be 4 bits here, because there we took 16 frames, here only 8 frames, so it is 3 bits. That's all. So the total address will be 3 plus 2. Okay, it's not going to be 4 plus 2, it's going to be 3 plus 2, 5 bits of physical address. So, and I'm sure you should be able to now, if I show you the entries here, then you will know that which page is where. Now M and OP is this page and happens to be in the frame number here. Now in the page table 0, 1, 2, 3. Now where is this page 3? It is here. Now what should be the page table entry? It should be the frame number. It should be 2. Now how many bits? It should be 3 bits, because totally there are 8 frames. So this is the maximum range. So 2 will be 0, 1, 0. It's not a next number. So this should be the entry here. Then I extract out this 0, 1, 0. And then if I am accessing maybe the second byte, which will be 0, 1. So my address will be this. Okay. So which will be this particular byte n. Okay. I am accessing n. Now is this address correct? You can see that 4 here, 4 here, 8 are gone. Then this is 0 to 3, then up to 7, this is 8 and this is 9. Now this value in terms of binary, it is 9. Okay, so exactly this will map to this particular location. So the simple binary number if you think and freeze it and think about it, you will be able to appreciate this. Now let me, for clarity purpose, let me remove it. So this is going to be the entries there. Okay, third page is going to be in the second frame, and the entry will be 010. Remember, it is not just 10 because 3 bits are required to represent the complete frame. It could be from 000 to 111. Now this is explained in terms of picture. Page number is extracted as I told you. Offset is directly taken and fitted into, appended with the physical address. Page number has to be replaced. Now, where is the page table? It needs to be in some memory, and imagine that I have a register which will be pointing to the address where the page table itself is physically there. Okay, so in that case, it will be the starting of the page table. So I am indexing into it. Okay, that means all the subsequent bytes or it's not even bytes. Okay, remember, everything is an entry. The number of entries are not byte wide. It could be 10 bits, 14 bits, 16 bits based on the entry in each table. So imagine it to be an index into the table. Okay, you have a table, okay, which is changing from 0 to whatever the number of pages are. So what is the content inside the page table, how many bits are there, it depends on the implementation. So don't think that it's only a byte or it's a bit or it is exactly a frame number. No, there are going to be more entries in the page table. So assume that there are some entries, PTE, page table entries, is going to take up some bits, and you are going to use the page number to index into it. And if the page itself is residing in a memory, your page table base pointer, page table PTR, is going to point to that, and then it is, I add that with the page number, then you will be directly indexing into that entry, and you will extract out the frame number. Now, based on how many bits are reserved for frame number, depends on the number of frames, you will extract that many number of bits. You have to keep that much of bits and take that out, append it with the offset, you generate the physical address. So that is what is coming out of finally from the CPU, assuming MMU is inside and addresses are generated, page table is consulted, page MMU is holding the page table converted, or sorry, entry of the page table. Page table itself is not going to be an MMU. Remember, MMU is a mechanism to convert the page number into frame number. But page table itself is a huge structure, depends on what is your logical memory addresses and how many indexing is, how many entries are there and how many bits are there for each of the page table entries. It's all very dynamic and depends on the implementation. So somehow you assume that the frame number is brought into the MMU and it is getting accessed by accessing the page table, which could be in a memory somewhere again. Okay, there is some mechanism called TLB which I will talk about shortly. Till then, assume that you have a page table located somewhere and you access it by indexing into it using the page number, extract out the frame number, and depends on how many frames are there in bits, then append it with the offset. With the offset you are not going to touch it. Whatever the CPU wanted, that offset within the page is available within the frame, so you have to access the same particular byte. So you access it. Okay, that's it. So this, if you understand this particular conversion, then I think this lecture is taken care of. Okay, so this is how conversion happens. You index into the page table using the page number and extract out the frame number, append it with the offset, and generate the physical address, which is corresponding byte within the tree. So whatever is shown here, more pages, that's larger footprint of the process. And what does each entry in a page table correspond to? Each entry has a corresponding mapping of a page of a process, okay, in the increasing order of its virtual address. Okay, please remember the page number is in the increasing order. If you are the base pointer is assuming that this is the starting point and then this is the offset, the page number is given here. So page pointer, actually table pointer will be pointing here, and then you are adding the n bits to, this is a binary addition. Okay, imagine this is a addition to the offset. Suppose your page table is itself is residing in 1000, and the page number, imagine that each byte is the entry in the page table. Then your page number says 4, then address 4 will have the page table entry for the page 4, and then again 1005 is the next page table page number, and it will have an entry. Remember, each number increment of page number needs to be there as an entry into a page table. Okay, that is very important for you to remember that. So that's it. So from the logic letter, the page number is extracted. Page size gives number of bits for the offset field. Then page number is used as an index to access the page table entry PTE of the page. Okay, every page has an entry within the page table where a particular address range falls within. Okay, based on the logical address, the page number will be decided, and then from the PT you extract out the frame number part, and again number of bits you reserve or store within the page table depends on the number of frames you have on the physical memory, and use it along with the offset. That is, appending it to the offset, you generate the physical address. Okay, that's it. See you in the next lecture with some more information about the page table entries. Bye bye.